Power system blackouts represent the ultimate failure of a nation's electrical infrastructure, occurring when the balance between generation and demand is catastrophically lost. This analysis explores the causes, international experiences, and modern prevention strategies required to maintain grid resilience in an era of rapid energy transition. A blackout is defined as the total loss of power to a specific geographic area, often involving the disconnection of thousands of megawatts of load from the grid's generators. Unlike local outages, blackouts are frequently characterized by wide-area disturbances and system separations where the high-voltage transmission grid is forced out of service. These events rarely happen instantly but rather develop through a series of complex events and technical failures that cascade across interconnected regions. The societal importance of electricity cannot be overstated, as modern life is fundamentally dependent on an uninterrupted supply for water purification, food preservation, and communication. Economic losses from blackouts are massive, leading to industrial shutdowns, the failure of hospital life support systems, and the total paralysis of transportation networks. Beyond economics, prolonged outages pose a significant threat to national security and public safety, especially during extreme weather or political instability. The anatomy of an electrical grid involves a delicate coordination between generation, transmission, and distribution systems managed by control centers using SCADA and EMS technologies. Historically, the evolution of blackouts has shifted from simple mechanical failures in the 1960s to complex, market-driven, and renewable integrated crises seen in the 2021 Texas storm and the 2025 Iberian collapse. These events are classified based on their origin, including natural, technical, human, cyber, or market-induced factors, each requiring unique defensive responses. The major causes of grid failure typically begin with initiating disturbances such as equipment failure, weather events, or operator error. Empirical data from Europe suggests that weather is the most common initiator, responsible for over 30% of serious events, while grid instability remains the most damaging in terms of total power loss. Blackout development follows a specific progression from a normal state through a disturbance to the redistribution of power flows, which may eventually lead to a total collapse. Cascading failure theory explains how the sequential tripping of one component, often due to thermal overload or voltage decline, places unbearable stress on remaining elements. This chain reaction causes the system to separate into isolated islands, most of which lack sufficient generation to remain active. Maintaining the supply-demand balance is a continuous physical requirement where grid frequency, typically 50 or 60 Hz, serves as the primary indicator of system health. Frequency stability refers to the grid's ability to maintain this set point,